Welcome back to Talk Tensors, the show where we delve into the fascinating world of machine learning research. Today we're taking on a paper that really caught our eye, an efficient framework for crediting data contributors of diffusion models. It's a bit of a mouthful, I know, but the ideas in it are really pushing the boundaries of how we think about data, especially in this age of AI.
Yeah, I agree. This paper really tackles a crucial question that's becoming, well, more and more relevant as diffusion models become more widespread. Like, how do we give proper credit to the people whose data made these models even possible in the first place?
Right, like we're in this new era where data is like the fuel for innovation, but we haven't figured out a good way to acknowledge and reward the people providing that fuel. This paper offers a pretty ingenious solution. I have to admit, I was quite impressed when I read it.
Yeah, it's a clever combination of game theory with some very practical machine learning techniques. But before we get into the nitty-gritty of their methods, maybe we should take a step back. Make sure everyone listening is on the same page about what diffusion models are and why they're so important these days.
Okay, so back to basics for a minute. Diffusion models have really exploded in popularity in the past few years, haven't they? They're behind all sorts of incredible things like, AI-generated art or creating images that look so real they could be photographs.
Yeah, they've completely taken over the AI world, and for good reason. They're incredibly powerful and versatile. But the core concept behind them is actually pretty intuitive. Imagine you take a perfectly clear image and you start gradually adding noise to it, kind of like static on an old TV screen. Eventually, the image becomes completely buried in the noise. A diffusion model learns how to reverse that entire process.
So it's kind of like cleaning up a messy signal, extracting that original image from all the noise.
Exactly. It learns to slowly remove the noise, bit by bit, until it builds back the original image. Once it's got that process down, it can create totally new images by starting with random noise and then denoising it based on all the patterns it's learned.
That's a really neat way to think about it. But where does the data fit in? How does the diffusion model actually learn those patterns you mentioned?
Well, that's where the datasets come into play. A diffusion model is trained on a huge data set of images. And by learning to reconstruct those images from noise, it basically learns the underlying statistical properties of the data. It learns what makes a face look like a face, what makes a landscape look like a landscape, and so on.
So the quality and variety of that data set are super important then. If you only trained a model on a bunch of landscapes, it wouldn't be very good at generating faces.
Exactly. And that's where this whole question of data attribution becomes so crucial. If we want these models to generate a wide range of outputs, we need diverse data sets. And we need to make sure that the folks contributing to those data sets get the recognition and rewards they deserve.
Because honestly, putting together these high-quality data sets is a ton of work. It's more than just taking a few pictures on your phone. It's about carefully picking images that are, representative and diverse and making sure they're labeled correctly.
Absolutely. And a lot of the time, this work is done by people who aren't actually part of the research labs or companies building these models. They might be volunteers, freelancers, or just enthusiasts who are really into AI.
And their contributions are really the foundation of it all. Without them, we wouldn't have all these amazing AI tools and applications. But the problem is, it's been really hard to measure how much each person's contribution is worth.
Exactly. It's like having a group of bakers making a cake. Everyone adds their ingredients and their skills, but it's tricky to pinpoint exactly how much each person's contribution impacted the final product. Was it the flour, the eggs, the baking technique, or a mix of everything?
That's a great analogy. And that's exactly the problem this paper is trying to solve. How do we accurately and fairly attribute the deliciousness of that final AI model back to the individual bakers who provided the data ingredients?
And that's where this concept of global model properties enters the picture.
Okay, I'll be honest. When I first saw that phrase in the paper, I thought, uh-oh, here comes the jargon. But your analogy definitely helped me understand it better. It's not just about how well the model performs on a single task or a single image. It's about its overall capabilities, right?
Exactly. It's kind of like evaluating the overall skill of that team of bakers, not just how well they did on one particular cake. Global model properties look at things like how many different outputs the model can generate, how good those outputs are overall, and even how well it adapts to new data it hasn't seen before.
So, for example, if we're talking about an image generation model, a global property might be how well it captures the variety of faces in a data set, or how realistic the textures are in the images it creates.
Precisely. And the main point here is that these global properties are directly shaped by the data the model was trained on.
So if we want to figure out how valuable each data contributor is, we need to understand how their data influence those global properties.
Right. And that's where things get a little complicated. Because diffusion models are so computationally demanding, it's not really practical to retrain them from scratch every time you want to figure out the impact of one person's data.
So how did the authors of this paper get around that problem? They weren't baking cakes in the lab, were they?
No cakes were harmed in the making of this research, but they did come up with a very clever solution. They borrowed a concept from game theory called the Shapley value. The Shapley value. It's basically a way to fairly distribute credit in a collaborative effort. Think back to our bakers again. The Shapley value would tell us how much each baker added to the overall deliciousness of the cake, considering all the different ingredients and skills they brought to the table.
Okay, I see how that could apply to data contributors, but how on earth do you actually calculate the Shapley value for something as complex as a diffusion model? I mean, we're not just measuring cups of flour here, right? We're dealing with millions, maybe billions of data points.
Yeah, that's where the authors really get clever. They use a combination of techniques to make these calculations manageable. One of them is called model pruning.
Pruning. I'm picturing a gardener, snipping away branches to help a tree grow stronger. What's that got to do with machine learning?
It's a surprisingly accurate analogy. In machine learning, pruning means getting rid of connections in a neural network that aren't as important. This makes the model smaller and faster without losing much of its performance.
So they're basically simplifying the model to make it easier to work with.
Exactly. They start with a fully trained diffusion model, and then they carefully remove connections that aren't really essential for making those high-quality images. The result is a smaller, more efficient model that still does the main job it was trained to do.
Okay, but how does that actually help them figure out the Shapley value for each data contributor?
That's where the second technique comes in, fine-tuning. After pruning the model, they fine-tune it on different datasets, each one representing the contribution from a specific group of data providers. This lets them see how each group's data affects the model's performance.
So instead of retraining the whole massive model for each combination of contributors, which would take forever, they're just tweaking a smaller pruned version.
Exactly. It's way more efficient, and it means they can do a lot more experiments to get a more precise estimate of each contributor's Shapley value.
That's really clever. So they've got this streamlined model, they tweak it with different data sets, and then they use this Shapley value idea to figure out who contributed the most to the model's capabilities. But did they actually put this to the test, like in a real experiment?
They did. They ran a bunch of experiments using 3 different data sets, each designed to highlight a different angle of data attribution.
Can you walk us through those experiments? I'm really curious to see how all of this works in practice.
Sure. The first experiment used a data set called CFAR20. It's basically a collection of images that have been labeled by different people. The focus here was on image quality. They wanted to see how much each labeler's work contributed to the model's ability to create clear, high-resolution images.
So were they able to pinpoint those star labelers, the ones whose data had the biggest impact on the image quality?
They were. And what's interesting is that the best labelers, according to their Shapley value calculations, weren't the ones who labeled the most images. They were the ones who consistently provided clear, accurate labels. It suggests that data quality is just as important as quantity, if not more so.
Makes sense, you know what they say. Garbage in, garbage out. What about the other experiments? What other data sets did they use?
The second experiment used a data set called Celeba HQ. It's a collection of celebrity faces. This time, they were interested in diversity, how much each celebrity's data helped the model generate a wide range of different faces.
Now, this is where it gets really interesting, right? Because we're not just talking about technical quality here. We're talking about representation, inclusivity, all of that.
Exactly. And their findings were really fascinating. The celebrities whose data was most valuable for creating a diverse set of faces were often those from groups that are underrepresented in data sets.
So their data was key to making sure the model wasn't just producing the same kinds of faces over and over again.
Precisely. It really highlights how important diverse data sets are, not just for technical reasons, but for social and ethical reasons too. We want these models to be able to represent the full range of human diversity.
It's a really powerful reminder that the data sets we use to build these AI models have real-world consequences. Okay, so we've covered image quality and diversity. What was the third experiment all about?
For the third one, they used a dataset called ArtBench, which is full of post-impressionist paintings. This time, they were interested in the aesthetic side of things, how much each artist's style contributed to the overall look and feel of the images generated by the model.
So it's like they were trying to figure out which artists had the biggest influence on the model's, artistic eye.
Exactly. And what they found was intriguing. The artists whose data proved most valuable were often the ones whose work had really vivid colors, bold brushstrokes, that sort of vibrancy. It kind of suggests that the model was picking up on these artistic qualities and using them in its own creative process.
It's almost as if the model was learning to appreciate art, to recognize what makes a painting really visually striking and engaging.
It's a really cool peek into how these models work, and it raises all sorts of questions about the nature of creativity and how data influences artistic expression. But before we wander too far down that philosophical path, maybe we should bring it back to the paper's methods. Did they do anything else to double-check their findings?
I'm always a fan of those sanity checks in research.
Yeah.
Did they do anything to make sure the results weren't just a fluke?
They did. They ran what's called counterfactual evaluations. Basically, they took the data from those top contributors we talked about and removed it, then watched to see how the model's performance changed.
So they're asking, what would happen if we took away the most valuable data? Would the model still be as good?
Exactly. And in all three experiments, removing the top contributors' data led to a noticeable drop in how well the model performed. That gives more support to the idea that their Shapley Value approach is really pinpointing those most valuable data contributions.
That's a pretty convincing validation. So they've shown this method can accurately identify the most valuable data contributors across different data sets and tasks. But what's the big picture here? Why should our listeners care about all of this?
That's a great question. And this is where things start to get really exciting. You see, this paper isn't just about giving credit where credit is due. It's about changing how we think about data in this age of AI. And it's especially important for all the people out there who are creating, sharing, and using data every single day.
It feels like we're right on the edge of a huge shift in how we see things. Data isn't just some raw material anymore. It's becoming a valuable asset, a kind of intellectual property that can be measured and rewarded.
Exactly. And this paper gives us the tools to start figuring out that value in a way that's both accurate and fair. Imagine a future where artists get like micropayments every time their style pops up in some AI-generated artwork.
Whoa, that'd be amazing. Or imagine data labelers getting paid based on how much their work actually improves a model's accuracy.
Exactly. It could completely change how we think about data ownership and who gets compensated.
We're moving away from this idea of data as a free resource and towards recognizing it as a valuable asset, something with real economic worth.
Right. And this paper gives us a framework for actually quantifying that worth in a way that's, rigorous and transparent.
It's like a powerful tool for building a data ecosystem that's more fair and sustainable.
Absolutely. But we shouldn't get too carried away just yet. There are still some hurdles to overcome.
Like what? What are some of the challenges?
Well, using this method on those truly massive data sets, the ones with billions or even trillions of data points, that's going to require some even more efficient computational techniques.
I bet there's a lot of research going on in that area right now.
Oh, absolutely. Researchers are always pushing the limits of what's computationally possible. And then there are those tricky legal and logistical questions around data ownership and intellectual property.
Those are the big ones. Like who actually owns the data that's used to train these models? And if an artist's style is used to create a new artwork, who owns the copyright?
Yeah, those are tough questions. They're going to require a lot of careful thought from policymakers, legal experts, and the whole AI community, really.
It feels like we're stepping into uncharted territory, and this paper is one of the first maps we have.
It is, but it's an exciting landscape, full of potential for innovation and positive change.
Speaking of possibilities, let's zoom out for a second. This paper focused on image generation. But these days, diffusion models are being used in all sorts of other fields.
Oh, yeah, they're popping up everywhere, from healthcare to drug discovery, even material science.
Can you give us a few examples of how they're being used in those areas?
Sure. So in healthcare, they're using diffusion models to generate super high-resolution medical images that can help doctors diagnose and treat diseases more effectively.
I've also read about them being used to design new molecules for drug development, which could, speed up the search for new cures and treatments.
And in materials science, they're being used to design new materials with very specific properties, which could lead to breakthroughs in things like energy storage and renewable energy.
Wow, this technology has the potential to really shake things up in a lot of industries.
And as diffusion models become even more powerful and more common, this whole question of data attribution is only going to become more crucial.
Because the stakes are getting higher.
Yeah.
If we're going to rely on these models to make decisions that affect people's lives, we need to be sure they're built on a foundation of data that's been fairly and accurately credited.
It's about making sure everyone who contributes to AI's development shares in the benefits.
Before we wrap up, I want to go back to something you mentioned earlier, the history of data attribution. Was this paper like a total breakthrough, or were there other attempts to tackle this problem before?
Oh, that's a good question. This paper definitely represents a big step forward in applying Shapley values to diffusion models, but it builds on a lot of earlier work in data valuation and collaborative learning.
You talked about federated learning a little bit before. Could you tell us a bit more about that?
Sure. Federated learning is a way for lots of devices or servers to work together to train a model without actually sharing their raw data.
So instead of sending all the data to one central server, the training happens locally on each device.
Exactly. And that's really useful in situations where data privacy is a big concern, like healthcare or finance.
But it also brings up questions about how to fairly measure each participant's contribution.
Precisely. And that's where methods like Shapley values can come in. They can be used to figure out how much each participant's data helped the overall model performance, even though that data never left their device.
So this paper is part of a bigger movement towards finding ways to fairly value and reward data contributions in all sorts of collaborative settings.
And it's a movement that's gaining momentum as AI becomes more and more woven into our lives.
This conversation has been really eye-opening. It's incredible to see how these, abstract mathematical concepts are being used to solve real-world problems.
It's a great example of how interdisciplinary thinking and the incredible pace of innovation in AI can work together.
This paper has given us a lot to think about, and I have a feeling we'll be coming back to these ideas for years to come. But for now, let's move on to our novel notions segment. This is where we take the ideas from the paper and try to push them a little further, explore some of the potential implications and future directions. So where do we go from here? What are some of the nascent extensions of this research?
Well, this paper focuses on fairly dividing credit, which is super important. But what if we kind of flipped the script? What if, instead of just measuring value, we could actually control it?
Control data value. How would that even work?
Think about those prune diffusion models we talked about. They're basically streamlined versions that focus on the most impactful connections for a specific task. What if we could prune a model in a way that emphasizes certain data contributions?
So instead of just observing which data is most valuable, we could actually shape which data the model prioritizes.
Exactly. Imagine you want a model to create images with a specific style. You could prune it to really focus on the data from artists who embody that style. You'd basically be amplifying their influence.
Wow, that's fascinating. It's like we're not just crediting data, we're curating it, almost like an art form in itself.
It definitely opens up a whole new level of control over the creative process. You could even use it to reduce bias in models.
By pruning away the connections that reinforce harmful stereotypes or underrepresentation.
Exactly. You could selectively boost the signal from underrepresented groups, making sure their contributions are not only recognized, but amplified.
It feels like we're shifting from data attribution to data empowerment.
Yeah, it's a powerful idea. And it has implications far beyond just art. Think about scientific models. You could prune them to prioritize data from certain experiments or researchers, basically customizing the model's knowledge base.
It's like creating bespoke models.
Yeah.
Optimized for specific tasks or research questions.
Yeah, it's a big change from how we do things now, where models are usually trained on these massive general data sets.
It also raises some interesting philosophical questions, like if we're actively shaping the value of data, who gets to make those decisions? And what does it mean for things like fairness and objectivity?
Those are really important questions. This kind of power needs to be handled carefully. We need clear guidelines and safeguards to make sure this technology is used responsibly.
It's like we're not just exploring a new technological frontier, we're navigating a whole new ethical landscape.
And as with any uncharted territory, there are bound to be surprises, challenges, and opportunities we can't even imagine yet.
This is what I love about these deep dives. They don't just shed light on the present, they fire up our imagination about what the future might hold.
It's that blend of technical understanding and boundless curiosity that really drives progress.
Well, this paper has given us plenty to ponder, and I have a feeling we'll be revisiting these ideas for years to come. Thanks for joining me on this deep dive. It's been a real pleasure.
The pleasure was all mine. Until next time, keep those questions coming, keep learning, and keep diving deep into the amazing world of machine learning.